Okay, good afternoon, everybody. It is with great pleasure to introduce today's speaker to you, Professor Marcel Merk, who's had a diverse trajectory. He's started in Nijmegen, then did a postdoc in Carnegie Mellon, then a postdoc back in Netherlands in Nikhef in Amsterdam, and then he's been in Utrecht as, I guess, a postdoc, and then in Maastricht, which is where he is now, well, 50-50%, and with Nikhef in Amsterdam. And today he's going to tell us about, I guess, Flavour puzzle, CV violation, and LHCb. Please, Marcel, the virtual floor is yours.
Thank you very much. I'm very happy that you invited me. I understand that you're an audience of a diverse audience of theorists, yes, including all sorts of cosmology, maybe statistical physics, I don't know, particle physics. So I thought, let me be brave as an experimentalist, and let me also have to talk on theory, which means that you can correct me wherever I go completely wrong. So I don't shy away from making some theory comments, and if you object to it, don't hesitate, just object.
Will do, thank you.
And then the excuse is that I'm not in Dublin myself, so I looked it up and I see these beautiful pictures on the web, where probably your institute is not, but it's more in town here at this building. Do you see my mouse, by the way?
You haven't actually shared your screen.
I haven't shared the screen.
Oh, not yet.
I'm an idiot. Sorry. Then I forgot this now. Okay. Do you see it now?
Yes, we do. Yeah, and we see the mouse.
Yeah, sorry. So yeah, I was hoping to come to Dublin and visit maybe this very nice area, but I think your institute is here at this building at the.
That's where we are. Yes.
Which I was always hoping to visit and discuss with you. And also, I must admit, I am a little bit a fan of Guinness.
Oh,
so
yes.
A long time ago, I went there at this beautiful place where you have the view over the city. I was hoping to do so, but I made a silly accident with sports, and I could not make it. My apologies for that. So to business, what I was hoping to do with you is to discuss what I call flavor puzzles and the LHCb experiment. Now, it's clear what the LHCb experiment is, but I would like to dive into these flavor puzzles and try to make a connection to the physics of the early universe. So what you see on the left top is indeed the history of the early universe, the timeline from left to right, where we are now at the right-hand side. At the left is very spectacular Big Bang event. And what we are hoping to do with the experiment, the LHCb experiment, is to learn about the fundamental physics that could have played a role at the electroweak scale, 10 to the minus 11 seconds after the Big Bang. What you see at the right bottom, this spray of blue lines there is actually an event in the LHCb detector, a bit artistically shown, where the collision is at the left-hand side of this thing, and then all these particles we produce flow out and are measured by subsystems at your right-hand side. Do you see the mouse? Okay, thanks. Now, I would like to spend a word on what we call these flavor puzzles. And on the left bottom, you see this cartoon of the standard model fields. And of course, we all know that the basic constituents of matter, the protons, neutrons, or the up quark, the down quark, the electron in the atoms, and the neutrino. And nature, by some miracle during this very early phase of the Big Bang, gave us 2 and 3 generations of identical fermions. They're really identical, the second and third generation, apart from the mass of the particle. But the quantum numbers are identical. The forces they feel are identically introduced. I will comment on that a bit later. And the question really is, why do we have these 3 generations of particles? And that's one of the issues of the flavor puzzle. Why these 3 generations if we don't use them in everyday matter? The other obvious thing that I'm sure you also know is the universe is full of matter and there's no antimatter. Why not? How did that happen? Is there some explanation that we can investigate with experiment and then maybe implement in our theories of the early universe? And thirdly, we have these particles on the left-hand side, but here at the right-hand side, you see them sketched, and you see the masses. So you see the first generation particles are very light. The second generation particles are a little bit more heavy, but the third generation, and in particular the top quark, are really quite heavy. And where does this particle mass hierarchy come from? So that's what we are investigating in this flavor puzzle. Let me continue. Yeah. So this is the outline of the talk, and it's a bit ambitious. And you tell me you have a bit of time, but tell me when to stop, or I can also stop after point 3, and we can see how it goes. But what I was planning to do is to go through the issue of 3 generations and the origin of CP violation. Maybe you all know it, and then I will go faster. Spend some comments on how much CP violation do we actually have in the standard model. How do we gauge that? Then I come to the more experimental side. What are the measurements that we are doing with the LHCb detector on CP violation? And then to point 4, we have recently seen some strange features of the events happening in beam meson decays, which we call Flavour anomalies. And I will comment a bit on the status of that, and then I have a short outlook. Okay, let's go with the first one. 3 generations and the origin of CPV. You see it already on the right-hand side. We lost this antimatter, and happened 13 billion years ago. The first question is, how do we know that we actually have 3 generations of fundamental particles? I make a nice sketch there, you can see it, but is it really so? And the reason that we believe this is so goes back to the lab collider that was taking data at CERN between 1989 and 2000 in this period. And in this lab collider, what we did there, we created E plus C minus collisions with the Z0 boson. And the Z0 boson, the carrier of the weak force, decays in any fermion-antifermion pair light enough to be created. And so we can test that and see in which particles this Z boson decays. Now here you see a curve with a measurement from the time. A sketch on the left-hand side, and this plot is an event display of the Delphi detector. And what you can measure is from the amount of events that you observe, you can measure what we call the line shape of the Z boson. So as a function of the beam energy, which you see plotted here, the beam energy of the colliding electron-positron pair, you can measure the amount of Zs you produce. And then you will see a curve that actually will depend on how many neutrino generations there exist. If there are more neutrinos, then the production cross-section is higher because the Z can decay into more states. It's a wider curve. And if there's less neutrinos, it's the blue curve. And the yellow is the 3 neutrino family curve. And you see the data points exactly match that. And from that, at the time, we draw the conclusion that the number of neutrino generations is 3. In fact, you could also say, we also see that we don't decay in other leptons, charged leptons of a 4th generation, but you could never exclude them since they may have a mass higher than the Z, in which they wouldn't decay. So the Z, for example, does not decay into the top. So we know that there's no additional weakly interacting light fermion generations. That was step 1.
May I jump in with
Sure.
a question? Yeah.
Sure.
So this was our understanding at the time, right?
Yeah.
So this was just, the number of families of light neutrinos was constrained by this, but we can't say anything about right-handed neutrinos or heavier. Yeah.
So the only thing you say here that for the particles which couple to the V minus A theory of the weak interaction of the Z decays, there are no more standard model type neutrinos that couple to the Z. If something doesn't couple to the Z, you don't see it.
Sure.
So that's a different story.
I also had a question on your very first slide, if I may.
What?
The beautiful cartoon that you had here.
Oh, this one.
So you say that the antimatter, well, this guy claims that the antimatter disappeared 13 billion years ago. Is that definitely what we think, or do we have the possibility of, I don't know, warm inflation that could carry on for ages, and we still produce some, CP violation later on, which would lead to some antimatter?
Which would, you mean now that it disappeared later on, or that it's now still around and we don't see it?
Oh, no, that it disappeared, but closer than 13 billion years ago.
Yes, so I probably if you think of a brilliant theory that does that, then you need also some experiment to actually prove you're right or wrong. And at the moment, I don't know of any of this development, but this I don't know, to be honest. I mean, later then we have various. So I come to that later, but I think you can talk about at the gut scale where you do processes. You can talk about seesaw mechanism with neutrinos. You can talk about electron baryogenesis, but even at B meson level baryogenesis, there are ideas. But I don't know anything that goes beyond seconds of the Big Bang. Maybe because it's you need a process of sufficiently high energy to do this. So I don't know. Is my answer.
Okay, but so you said you would need an experimental probe for it. So it doesn't look like we would have any experimental probes for it, right?
Yeah, first you have to tell me what to look for. Now, what should we look for?
So
you want to see some remnant, right, of a process. For example, if you look for supersymmetry, now you can still look at the core of stars, where maybe neutralinos collide, and you can see them annihilating or so. But in this case, you need a model, and you need to test it on some experimental feature. And I don't know the answer.
Okay, thank you.
Oh, thanks for the question. What I wanted to say here is that you see not just that it's the 3 neutrino curve, the yellow one fits better, but what we also measured, and I don't show it here, is that the number, you can actually fit the number to a floating point number, and it's 3.0. It's not 3.1, it's not 2.79. No, it is 3.00 within 5% or so. And so with precision. So we know that there are the 3 neutrino case is the best, but it's also not that there's something slightly deviating from the model. It is really described by 3 neutrinos, which I think is a good thing to know.
Sorry, could I ask a quick?
Sure.
What mathematical tricks do you have to do to have like 3.1 neutrinos?
So, I mean, there I would even challenge you. There's many theorists who come up with all sorts of ideas. Something that couples differently than a neutrino. You know, if you have something with a different coupling constant, you can do anything, right? So if the coupling constant is 10% of the neutrino V minus A coupling constant, then you get that, right?
Okay.
So, does that answer your question?
Yeah, I guess I was wondering if it was something more fancy, like some analytical continuation. But yeah, that would also make sense.
I mean, I'm sure one can think of many cases to do so, but the point I wanted to make is that indeed the standard model describes exactly the data that we measure. That's the comment I wanted to make. Then go to step 2, and that's much later with the LHC. And at the LHC, we measure the production of Higgs particles. And the dominant diagram for the Higgs is this gluon fusion loop that you see here, where actually there's the gluons are taken out from the colliding protons. The Higgs is a proton-proton collider. From the protons, you take the gluons, they collide, and actually they couple via this triangle diagram, which is a virtual fermion loop. And then at the fermion vertex here, you produce the Higgs. Now this production goes proportional to the coupling of the Higgs field to the fermion, which is why I wrote a T here, because that's the heaviest fermion we know with the largest coupling. Actually, the coupling is 1. And then if we would have a heavier fermion than the top, heavier standard model fermion, the amount of Higgses we would produce would be larger. And we can compare our calculations at the time with whatever we saw from the discovery of the Higgs. These are the very early curves from the Higgs discoveries of the Higgs events to 2 photons and the Higgs to 4 muon curves here. And there you also see that the prediction of the cross-section of the Higgs field, the Higgs production, kind of matched with the data. So from that we concluded that the top is the heaviest fermion. So we now know that there's nothing beyond the light neutrinos, but there's also no fermion heavier than the top around, which couples according to standard model, because that would also show up at the LHC. So at this point, we can say that for the standard model particles, 3 generations is what we have. The top is the heaviest, and we have these nice 3, what we call flavors. So that's the conclusion that we draw. Okay, let's go to the next step, and that's the concept of universality. what we see in the standard model is that we have these three generations, but they interact identically. So if you take, for example, electromagnetic interaction and between two electrons or two quarks or two protons, doesn't matter. If you take two quarks, then the generation index I, this is this generation 1, 2, 3, yeah, for the up and down, charm, strange, top and bottom. The electromagnetic force is the same, independent of the generation. The same is true for the strong interaction. It couples through color and has nothing to do with the generation index of these particles. The same is true for the weak force. The weak force also has the same feature as it is implemented, that it's independent of the generation. And the strength here is indicated by the square root of here alpha QED, alpha S, the Z coupling and the W coupling. But then comes the violation of universality, and that's the Higgs, because we know these three generations are not identical because of their mass. And that's explicitly clear, the masses are really very different. What I forgot to say above is that in this, the way these forces behave from the basic description of the theory, there is no matter-antimatter asymmetry present in these interacting fermion fields, and no CP violation by construction. We come later how this arises, and that has to do with the Higgs. So the Higgs actually is the particle that the Higgs coupling that violates universality with the masses, and that's done in this diagram that you see at the left bottom, where two different quarks, they couple with a certain strength to the Higgs, and this strength depends on the generation, and even more so, it actually couples between generations. So this Higgs coupling, also called the Yukawa coupling, actually does couple of different particles of different generations together. This Yij, where Ij is the generation index. So it's not universal, and it mixes generations. That's getting interesting. And even more so, if we if you look at this Higgs coupling to antiparticles, they couple with a complex conjugate coupling construct. And we come to that a bit later. We come back to that later. And that in the end gives you the possibility to actually get CP asymmetries into your theory. At the CP mirror here, you have the particle coupling to the Higgs with the Yukawa couplings. Here you have the antiparticle couplings to the Higgs field. And the CP mirror can be different because of the fact that you have complex conjugate couplings here. It's not going to be easy to introduce it into the system, but we will see that it works.
Sorry, with the Higgs and the Yukawa's mixing generations, you don't mean the standard model Higgs,
Yes,
right?
this is standard model Higgs. But
The
this is
standard
the standard model Higgs, but what I will come to, this is, we are talking now of particles, I will say that in a second, as we introduce them at high energy before the symmetry breaking of giving mass to particles. So at this point, I have massless fields.
Okay.
And that's what I wanted to say. You're a bit ahead of me, so it's a very good question. We go now to the next slide where we see here again the history of the universe from the very, very high energy scales, grand unification, electroweak phase transition, and to on the top of it today. And we are now talking about this era here before the electroweak phase transition, before the mass generation with the Higgs, where all particles or fermions are still massless in the universe. Right? So then what we have a weak interaction that couples up to down, straight to charm, bottom to top, and these interactions, the W, are really identical and of the same strength, and there is no generation mixing into this system. This is what we now later, if you know about it, because you know about masses, but at this point, when you create it, there is no such thing. So it purely operates within one generation. Then we say, we have the Higgs. This Higgs actually allows this coupling between generations. And then at some point, the universe reaches this temperature of 240 GeV or so at the era of 0.01 nanoseconds in the universe. The Higgs develops a vacuum expectation value, and this vacuum expectation value then leads to the fact that we get massive particles. Now, how that works is the coupling that you see here with the Higgs field gets this VEV, this vacuum expectation value, the V. And what we can then do, we can redefine these particle mass states by diagonalizing the new system, the massive particle system, into a coupling which we call the mass coupling of the particles. So what we do, we have all these couplings Yj, the particles develop a mass, and then say, let us now re-diagonalize this Hamiltonian, this interaction of the Higgs, to make a diagonal. And so it's just a change of basis states into these particles we now know as the mass eigenstates. Now, when we do that, you can always say that, yeah, you can always diagonalize the system. And we do it in such a way that you then only, of course, have the interactions between the particles of the same generation. So no I to j anymore, because you diagonalize the system. And we did that by defining these new mass eigenstates, that's QIM instead of QI, which are now linear combinations of these masslet states. And these linear combinations, we call VUD, VUS, VUB. These are just parameters. In principle, they are free. And use them to go from one basis to the other basis. But when you do that here, and you write down your total Lagrangian, of course, you also have to do it in your interaction Lagrangian, because you have to work with the same basis everywhere. So when you do that, in terms of the mass eigenstates of the particles we know today, then we get this crazy system of a 3x3 matrix of couplings, and the weak interaction now works between the up and the down, but also an up and a strange, an up and a bottom, and you have these generation changing interactions. Now, since before we had these IYJ, which were complex couplings, we could actually get also these complex values into these VIJ elements that you see here on top. So, and that's how you actually start doing something that may introduce CP violation into your interaction system. So this all happens because you go to a universe that is cooled down. Maybe the phase transition here caused it. There are some theories I will comment on. Maybe not, we don't know. But this is now the system we work with. And what we see is that the weak interaction with mass eigenstates, or with the physical particles, they mix these generations. You have up to down transitions, up to S. All these transitions now happen because of these mass eigenstates. And the complex values of these coupling constants, who take care of all these interaction terms, they allow for CP violating phenomena only and only if there are 3 generations of fermions. This whole story would not work with 1 or 2 generations, because simply the amount of freedom is not enough to allow for complex couplings in that case. So it's getting very interesting here. 3 is the minimum, 4 would be also work, 5 would also work, etc. Interesting, I would say. So this is the flavor structure we have, comparing interactions with Higgs. The forces are by construction flavor universal. The Higgs interaction is not at all. It's mainly 3rd generation. And all the Higgs interaction goes into this top particle here. I just make a sketch of the mass of the particle on some logarithmic scale, I guess, to give you an idea. And the 3rd generation coupling is by far the largest one. And one of the other miracles I find, people say it's numerology, but I think it's interesting. The top Yukawa coupling, it's a dimensionless coupling constant, and it happens to be 1.0. So this top Yukawa coupling, this top Yukawa coupling could have been 10 to the minus 10, it could be 10 to the plus 20, but that value is actually 1.0. You tell me as a theorist whether it's interesting or not. I find it intriguing that this is the case. So the flavor puzzle is, what is the origin of all these Higgs couplings across generation? Where does this come from? We see the Higgs coupling is large for 3rd generation, small for 2nd generation, and tiny for the 1st generation, tiny masses. And it may be that there is some additional theory beyond the standard model, where new particles, new forces may show a similar deviation from flavor universality that we have in the standard model. And that's one of the things at the end of the talk that will come back. So that was the first part. I go now to the amount of CP violation in the standard model. And you give me a sign whether this is going too slow or too fast, and just correct me where you
It's going perfectly.
Okay. The amount of CP violation, how much matter-antimatter asymmetry is there? That turns out to be not a trivial question. Let's go back to the flavor changing interactions of the W boson. So here you see the typical diagram simply of a down quark decaying into or coupling to a U quark and a W boson. And the strength of this thing is this element VUD that we just introduced before via this generation mixing of this Flavour eigenstates to mass eigenstates. And then there's an overall coupling strength G, the weak interaction, which is related to G fermion, the weak interaction coupling constant. Now these interactions inside a single generation from up to down, charm to strange and top to bottom, they are all quite strong, and this VUD, VCS and VTB coupling constant is typically 1. So they are strong. These are big couplings. If you go from the first to the second generation, then you come to VUS and VCD, then it turns out these lines are a bit thinner, meaning the coupling strength is not so strong. It's getting it's less it's happening less frequently. If you go from the 2 to 3 generation, you get VCB and VTS, VTS and VCB. That's this coupling here. Again, the lines are thinner, which means that the magnitude of these constants is again smaller. And finally, if you go from 1 to 3 or 3 to 1 at the left bottom and the right top of the matrix, the couplings are even stronger. So there's a clear hierarchy in this matrix. Now, if you make the CP mirror of these things, basically through CPT, you reverse the arrow of time. There's something goes here. Sorry. You get complex coupling constants. So instead of this coupling VUB here, you have VUB star. And that indeed gives you the possibility to do something with these coupling constants, complex coupling constants that we will see later. So the CP violation is caused by these complex coupling constants.
Sorry, may I
Yeah.
ask? So on the previous slide, when you were saying you call coupling of top is 1, which is very intriguing, don't you think it's also intriguing that the interactions VUS and VCD are of the same order of magnitude?
So basically what it means here by the same VUD, VCS, and VTB, you mean this diagonal is basically 1?
Yeah, no, I mean the off-diagonal ones. The fact that the 2-3 and the 3-2 interaction are of the same magnitude. So the 2 gray lines that you've drawn have the same thickness. I don't know, to me that's also quite intriguing.
So yeah, so what we are actually seeing here is we are seeing the amount of rotation of the interaction eigenstates to the mass eigenstates. And if you think only of a 2 by 2 matrix, then you have only a cosine theta and a sine theta.
Sure, yeah.
And they are related. So there's the 1 plus and 1 minus. So the 2, 3, and 3, 2 are related. Now here you have a 3 by 3 system. It's get a little bit more complicated, but you have these unitarity relations there.
Yeah.
So you have a certain number of freedoms, and that is what I wanted to do next. I think basically you're still ahead of me with one slide. Very good. This is a parameterization of this matrix due to Lincoln-Wolfenstein. And what you see here at the left top is again the matrix where the squares give you an idea of how large the numbers are, where the big ones are 1. And what Wolfenstein did, he saw the structure in the matrix, and he used the fact that since it's a rotation matrix, it must be unitary. So you can calculate the amount of freedom that you have in such a 3 by 3 system. And it turns out that if you make an expansion, assuming that the second order, the 1 to 2 is 1 order smaller than the 2 to 3, and the 2 to 3 1 order than the 1 to 3, then you can get this structure in this parameterizations with lambda, a, rho, and eta, where these lambda, a, and rho are real numbers. And you can compare these degrees of freedom with the 3 Euler rotation angles that you can make in a 3 by 3 system. And then the 4th degree of freedom you have left, you can show why you need 4 degrees of freedom for this, but it's not so important now. 1 is a complex phase. So you have 1 imaginary parameter in the system. So 1 complex phase, and that 1 parameter, which is here eta, that then should describe all CP violating effects you can ever see in nature if the standard model is correct. And so there's only 1 degree of freedom for this complex value of the coupling constants. if I go to the case where the universe would have 2 generations only, in that case, we would not have a bottom quark, not have a top quark. The rotation matrix would be very simple. It would have this form with the expansion parameter lambda, and our universe would not allow CP violation. At least the interaction, the weak interaction of the standard model would not allow CP violation. So I find that interesting. So there's 3 generations is the minimal particle content to generate CP violation in the standard model. Okay, so that's one thing. Now we go to the next step when we are measuring these CP, the amount of CP violation. What we do is we take this CKM matrix, and the fact that it's unitary, we can just express simply by V dagger V equals 1, trivial. So you write V dagger times V equals 1, and let me just take one of these relations. So these are 9 relations. In total, you have 9 complex numbers, 18 free degrees. Then you get 9 relations, and you have some other unmeasurable phases, which is why you come to these 4 degrees of freedom. But let me take one relation, and I take this one, where this row times the third row times the first column gives 0. That's one of the 9 unitarity autonomality relations. And then you see that these, remember, these are these coupling constants of the weak interaction, so they are just complex numbers. And so VUB times VUD plus VCB times VCD, VTB star times VTD, that's a relation, and the sum of that is 0. Now, since they're complex numbers, I show you here simply numbers like arrows in the complex plane. So this is just the complex plane. And so usually what we do in flavor physics, we define this horizontal part here, which is VCB star times VCD. We renormalize this number to 1 just for graphical purposes. Mm-hmm. And then in this plane, this is then the VTB star times VTD complex number, and this is the other one. So you get a triangle. When do you have CP violation, or when you have a complex interaction, is if this apex of the triangle is not on the real axis. So we must have some, some imaginary value into the system. And if you now take Wolfenstein's parameterization of this matrix with these 4 degrees of freedom, you can actually express the size of this triangle in terms of these quantities lambda, rho, and A and eta. So that's what you can do. And the reason why I'm doing that is that in the end, what I did not tell you is that these CKM elements themselves are not physical. They occur in a weak interaction current, and only combinations of values are physically observable. And actually, the physical observable ones are the combinations that are expressed by these angles here: beta, gamma, and alpha, the internal angles of the triangle. These are physical observables. The length of the vectors are observables, but you can rotate the whole triangle, meaning it would be the same physics. And we measured it. So this is the state of summer 2023. Here you see this rho and eta plane, as we call it. Here's a triangle, and there's various measurements that I will talk about later a bit that you can do to actually determine these parameters of the weak interaction, these complex parameters. And this is now the precision with which we know the apex of the triangle. Now, how much CP violation is there in the system? Now, if the triangle has more, if eta is bigger, then you get the bigger surface of the triangle. So an invariant of the amount of CP violation is the surface of this triangle. And the measurements we do is that we have many processes to measure these internal angles of this triangle, and they should all be consistent with this one single phase or this one parameter eta in the model. Now, about the amount of CP violation, in fact, this was I think I miss do I miss a slide? Yeah, I think I miss a slide, but it doesn't matter. So if you now think about how do we generate CP violation in the early universe, we have these forces, we have the standard model. So let's try and do it. Let's try to do baryogenesis at the electroweak scale. What you need is the Sakharov conditions. You need baryon number violation, you need C and CP violation, and you need thermal non-equilibrium. Now, in the standard model, everything is present. I did not talk about these barrier number violating processes, but this is due to an actual anomaly that was first calculated by 't Hoofd. And actually, you can make at high energy, you can make so-called Flavour transitions, which change your baryon and lepton number with the global anomaly. And these transitions, of which I'm not an expert, they happen frequently with a boundary of like 10 TeV or so. That would be the energy scale that you deal with. But they are there. They happen quite a lot. There's C and CP violation. We've just seen the triangle. So there are these CP violating weak interactions. And you could say the thermal non-equilibrium, this is done at the electroweak phase transition, where you go from zero mass particles to massive particles. And if my Higgs potential is coming down from a symmetric phase into a broken phase, which is this line here, then this transition, if this is a first order, is violent enough to have a thermal non-equilibrium and to generate this asymmetry. So here goes the Higgs particle to its VEV. And the idea is then in this early universe, but maybe you guys probably know this much better than I do. The universe would be in a symmetric phase before the phase transition. There would be these expanding Higgs bubbles where you have the broken phase inside the bubble, and at the end these bubbles grow, and you get this big broken phase. Now, unfortunately, this doesn't work in the standard model. Why not? The amount of CP violation is by far not enough. I will comment on that. And it seems like the mass of the Higgs is such that the phase transition is not a first order, which would be that you actually tunnel through your new minimum, but you actually slide down, and it's not violent enough to have a thermal non-equilibrium. So that's why people say this doesn't work in the standard model. You need something more. Now,
Sorry,
how much CP
can I just make a
violation?
technical point?
Sure.
It's not important, but the Higgs phase transition is crossover in the SM, not a second order.
Sorry, I missed the comment. Can you say it again?
In the standard model, the Higgs phase transition is a crossover transition, not a
Yes.
second order.
Yes,
Yeah.
I agree. Sorry. Yes, you're right. Apologies. Yeah, correct. So, but it's certainly not enough. Certainly not violently for first order. The amount of CP violation. How much do you need? Actually, we think that we need from observations of the cosmic microwave background that we need a barrier number asymmetry over the photon density, which is of the order 10 to the minus 10. And do we have that? You can ask, and that's also not a trivial question. How do you relate it to the surface of this triangle that is the amount of CP violation in the standard model? We actually owe that to Cecilia Janskog, who figured this out during, I think, a stay at CERN for a year when she focused on the problem and wrote a very interesting paper in 1987, where she could relate the amount of CP violation to this determinant of this mass square matrix. And what you get out of that is that it's 2 times the surface of the triangle J times the square of these masses. So the higher these mass differences are, the more CP violation there is actually embedded into the system. And if you now want to see how big does that give you a number, if you look at the early universe of a temperature of 200 GeV or so, then the amount of CP violation that comes out of these numbers, if you fill in these masses and the amount of energy, you get a value of 10 to the minus 20. Now, 10 to the minus 20 compared to 10 to the minus 10 is clearly too small. So that's why we generally say, look, it simply doesn't work. There's no thermal inequilibrium, and the amount of CP violation is not enough. So what we need to do.
This is very, very useful, because I always wondered when we say, it's 10 or 11 orders of magnitude too small, the amount of CP violation we have, is that if you assumed there was a first order phase transition in the standard model and you had electroweak baryogenesis, or it's very interesting that it had nothing to do with the process of baryogenesis. It's just due to the masses of these particles that
Yes. So it's not so much the surface of this J in this CKM triangle, but if you for fun say, let me get rid of the up quark and the down quark, and let me instead use two quarks of the fourth generation, like a new top prime and a bottom prime. And you fill in again these numbers where these would be twice as heavy as the top or so. You fill in these numbers, you would get there. It would not be so crazy.
Yeah.
So it's and when people speak about leptogenesis, they always say, CP violation lepton sector is very large, but you have the same thing. And what you need there, what people tend to forget, is you need these heavy Majorana neutrinos, and there you need the CP violating phases to make an invariant like this one. So, and because you have these very heavy Majoranas, then things go much faster if you compare them to an electroweak scale or so. So that's so in the end, an explanation requires new massive particles and of course some CP violation couplings as well.
So do you know that this value 10 to minus 20, was this also the Cecilia Yalska calculated this, or
Yes.
I thought it was, oh,
Yes.
okay.
So but the funny thing is, if you go back to the original paper, then she first tried an invariant which was linear in masses, but of course not with negative difference, it was linear absolute. And if you do that, you come very close to 10 to minus 10.
Oh, wow. Yeah.
But then what you now have to do, and I thought a lot about it, this here is a measure of a robust measure of the amount of CP violation. You can also go to the, to the fourth power or so. But why do we have squares in here? And the only argument I can think of as an amateur theorist is that somehow in your Lagrangian, you always have these quadratic mass terms. That's the only thing I can think of. But I'm an idiot and I'm an experimentalist. And if you have any suggestion there, I would be really interested to learn. But this is the reason, this is the real reason why we say it's 10 orders of magnitude missing. And also in explicit models that people build, it's always these quadratic masses that come back. I see that, but I don't know how fundamental that is.
I must say your slides are amazing. There's just so much information on those slides. I'm really enjoying it. Thank you.
Sorry about just my brain dump and.
No, it's fantastic. It's like very clear information, and there's a lot of valuable information.
Thank you very much. Thank you. So let me see if I can mess it up for you later on.
Sorry, just going back one slide.
Sure.
Is this why when people talk about leptogenesis with extra neutrinos, they sometimes need to have neutrinos of the mass like 10 to the 10 GeV, like because they need these large mass differences?
Yeah, I think so. So the point is this: if you go back to the first of all, you take the neutrino mixing angles. They are larger than the quark mixing angles. The neutrinos are more like a maximum mixing, while the quarks only mix very small. So this triangle that you create in the neutrino cases has more surface, but this is not the factor you need. This is like factors 4, 5, 6, maybe 10 or so. I don't know. This is not what you need. In the end, you need an invariant which is large enough, which you then have to compare to the energy of the universe during which the process is happening, because at that energy you have to create a unitless asymmetry, which actually does the job for you. And if you put these heavy Majorana neutrinos in this thing, then you will get there. And then you will certainly get there. So if you sometimes I think with the Dune experiment, we want to measure these CP violation in the lepton sector. This is great, but that's not the CP violation that you need in this Yarlskog invariant, because you actually need the CP phases of the Majorana neutrinos. And in some models, there are connections in this, but it is a different thing in the end. So I always find that very interesting to think about when people easily say, where we have neutrinos and CP violation, we have leptogenesis, but you also need these big masses to actually do it. So I don't know. But here my knowledge of the neutrinos ends. Yeah, so how do we search for these new massive particles? Two ways that I'm sure you know. You can go to the LHC or the big collider and actually try to produce more massive particles by raising the energy of the beams, and we call that direct searches with on-shell collisions, or called the energy frontier. This is done by the Atlas and CMS experiments, for example. While other experiments like LHCb, it's what we call the precision frontier, because there we want to use the quantum fluctuations in decay processes to do what we call indirect searches. I will come back to it, But you can imagine what you do here is if you consider, for example, a process at 5 GeV, the decay of a B meson, then you can write down the Feynman diagram of that. And if in that Feynman diagram you have a virtual particle of 1 TeV, you introduce that into your system, then maybe you get a slightly different decay rate of the process than the case where you only have standard model particles. So you look for these virtual effects of new very heavy particles coupling into the quantum fluctuations. Say, in other words, you use the help of Mr. Heisenberg to get your new particles. And that's what we do with LHCb at the LHC. That's what Bell2 does at KEGG, but also experiments, of course, like G-2 EDMs and what have you. Let's go to LHCb, because that's where I'm from. And, oh yeah, note to students, I forgot I put this in. At some point, as you say, you know, maybe we've learned already enough. Let's stop here. Just add an introduction and an illustration. The conclusion, you have a graduate thesis. Maybe that's the case. I don't know. Let's go to measurements of CP violation with LHCb. This is a drawing one of my PhD friends at the time made when he learned that I was going to work on the measurement of CP violation. He says, okay, let me draw you the measurement of the violation of the person CP here. And ever since I have this, I scanned it and I use it in many talks. I really love this. I told you that we have these complex coupling constants, and therefore we have CP violation into the system, which is great. But if you think about it for a microsecond, then you realize I write down a decay amplitude. Then I write the decay amplitude of the antiparticle. I take the absolute square of the two, and by definition, always get the same. You know, you have no CP violation because every decay rate is amplitude times amplitude complex conjugated. So what do we need to do? We have to make life is unfortunately a little bit more complicated. And we choose a process where we always have two amplitudes within the process. For example, the decay of a B meson to a positive kaon, a negative pion, has two amplitudes, which we here label as AT and AP, also called the tree and the penguin. And here is the tree diagram. And it's, you know, we call it a tree because it's, you know, there's no feedback into the system. It just loops into, it goes into branches. Well, for the penguin, we have this this topology here, and there's this famous story why this is a penguin, but I will skip that for another time. Now, once you have such a process, and you can choose it such that you have a coupling constant in here, which has a weak phase, which means that it's a complex conjugate phase for the antiparticle decay. So this phi here, here it's VUB, and if you go back to the earlier slides, then you saw that VUB is a complex value. So for the antiparticle, it's a complex conjugate. And if you now add gluons into the system, where the gluon contribution, this diagram and this diagram leads to also a phase, which we call the strong phase difference between these two diagrams, then you can do something very smart with that whole system. Namely, if you compare this process as a total for B0 to K plus pi minus with B0 bar to K minus pi plus, if you do that, then I write down here this amplitude, which is just the tree plus the penguin, and I put the two phases just at one side. You know, there's a weak phase here, and there's some gluons running around. I put it on one side. Then at the other side, for the antiparticles, I would have, so I assume now that the tree, the AT is real and AP is not. Then AT is here the same and AP is here the same, but I get a sign difference of the weak phase, the CKM phase of the particle versus antiparticle case, while this gluon phase at the two sides is the same. Okay, this is an amplitude, this is an amplitude. The decay rate is the square of these things, which is the absolute square. Here I just wrote it out for you. If you do that on a piece of paper, then you will see that because of this plus sign and the minus sign here, you get something which is different in the interference term. So these two things are the same, and the interference term of the two diagrams is where you get some sign difference. And the total asymmetry of this thing gets this value, which means that this phi should not be 0 and this delta should not be 0. If this is not 0, then you have CP violation. How do you see it? Easy. You go to the experiment, you look at this B to K plus pi minus, you look at B bar to K minus pi plus, you do an experimental measurement of what we call the invariant mass of the particles to extract a signal from the background. We do that for the particle and the antiparticle case. And then here we see that this one, happens more frequently than this one. We know that we produce the same amount of B and anti-Bs, but this happens more often than this one. Hence, this is CP violation. So this is how we actually measure a thing like this that we construct into the theory. But the measurement the message I have is that CP violation is always a pure quantum interference effect. So you always need, let's say, a double slit experiment with two amplitudes, in this case a penguin or a tree, and it's the interference of these guys that makes the difference between the matter and antimatter, always. So all CP violating phenomena result from a quantum interference effect. There's no classical equivalent. Whether you work on neutrinos, whether you work on quarks, I don't care. There's always CP, there's always this interference connection that does it. So my message there that I tell students always, in the end, we can go back to Feynman. Feynman says, in the end, all quantum phenomena are manifestations of the double slit experiments. Whenever you do some specific quantum thing, in the end, it's always similar to the interference in the double slit experiment. So here we would
Can I just ask a question?
Yeah.
So in the early universe, you could, in theory, have a CP violating vacuum. Like, would that also be a manifestation of the double slit experiment in this sort of view?
This you have to tell me again. In the early universe, you would have a CP violating vacuum?
Yeah, so if you have like a 2 Higgs doublet model, you can, in theory, have a CP violating vacuum at finite temperature.
Yeah. But in the end, you would produce the CP violation by a process. If you write down this process, and if it's a quantum process, then there is no way you can write it down in such a way that without interference, you create an asymmetry. And the simple reason is that one amplitude, the absolute square of one amplitude, is always the same as the absolute square of the complex conjugate. So you must have two contributions into the system somehow. Now, I don't know the detail that you are referring to. Maybe you know better than I do. But I would suggest have a look what really generates the CP asymmetry. Because I know of no example that actually does it within one. I cannot think of it. And in fact, I thought I had late at night when I was dreaming, when I'm in a semi-dreaming situation, I thought, CP violation and T violation are really very closely related due to CP-T symmetry. Now, and CP violation, you always need this quantum interference. Does it somehow give you also an error of time? This just because based on the fact that you have quantum interference and fundamental processes? I don't know. Just kept me awake for an hour and then I forgot it. But now I remember it again. So let's go to CERN, to the LHC collider, and become a bit more experimental. So this is, I'm sure you've seen this picture where with the Mont Blanc and the city of Geneva, and the LHCb experiment here is very close to Geneva. So we create some collisions here and we measure them. So we go to the LHCb experiment, 100 meter underground. This is the experiment, and we focus for this talk at least on the decay of B mesons. So B mesons are particles that contain this third generation B quark. And there are three types that we typically look at. It's the B plus, it's the B bar U, it's the B0, B bar D, and the B sub S, which is the B bar S meson. Now, what is nice to realize is that these B mesons typically have order of 1,000 different ways to decay. It's really incredible. You can go to pi plus, pi minus, k pi, j psi phi. You can measure k, pi, pi, pi. There's like 1,000 decay modes. And all of them can have some differences because of CP violation. And then, of course, it's constructed into the system. But if you add up all these 1,000 decay modes, in the end, your B and B bar meson will have the same lifetime, because a violation of lifetime, a difference of lifetime, would mean that you have CPT violation. And that you cannot have. So that's constructed into the system, but each of these 1,000 ones can have slight differences, but not the sum of them. And the very interesting ones, this is Murphy coming up, is that always the rare decay modes are the ones that are interesting. So the ones where you experimentally have to work much harder is the one that you should measure. Just a short word on the LHCb detector. There's a sketch here. I will show you a picture later. This is how such a spectrometer system looks like. If you look here at the sketch from the left, the collisions happen here. They're surrounded by a vertex detector, which very precisely measures the trajectories of the particles that are coming out of the collision. We have a particle identification system based on ring imaging Cherenkov detectors, which measure the speed of the particle through the gas medium. And if it goes faster than the speed of light in the medium, then it sends this Cherenkov radiation from which we can get the velocity of the particle. When we know the velocity, we measure in the magnet the momentum, and the two together give us the mass, so we can identify the particle. Again, here we have tracking detectors to measure the trajectories, and then we have detectors, calorimeters to measure the energy, and muon system to measure muons. So it's a whole complete detector system where we can reconstruct different particles and how they are produced. And here is the experiment. If you go to Geneva and you go into the experimental hall, 100 meters deep, then this is what you see. And if you look at it, you basically see nothing, because you just see a lot of iron and cables and infrastructure. But at the right-hand side here is where the interaction happens. And this thing from the right to left is a spectrometer. If I draw it on top, then this is the system you would see hiding behind the cables and the stuff. The vertex detector, the ring imaging Cherenkov, the big dipole magnets, again a tracking system, a ring imaging Cherenkov, calorimeters and muon stations. How does such a detector now work detecting particles? Here is an event sketched on top of it. So the collision happened here. Many tracks are produced all around, but at the right-hand side and above and below, we don't measure with this experiment. We only measure in one direction, because that happens to be better for B physics, for B meson physics. And you see all these particle tracks being produced in these detector elements, and the different colors give different particle types. Now, here I make a zoom of the collision point, and if you then make such a sketch, then this would be one detector layer of the vertex detector. And what we see are these cyan and the purple hits in our detector, and from that we reconstruct these blue lines, which are the particle tracks, and that's how we actually do it experimentally. This happens 40 million times per second, so we have to move our forces to get this going to find these rare events. So we reconstruct millions and millions of B particle decays. We select the interesting, which are often the rare ones, and then we, of course, often compare CP conjugated processes and to see what we get. That's how it experimentally do it. Now, if I would have to describe the strength and the weaknesses of this detector, this is a candidate of a very rare event of a B going into two muon particles. These are a mu plus and a mu minus from a B decay. Then the strength of the LHCb detector is really the resolutions with which we can reconstruct these vertices, because the detector is very close to the beam. We can measure the curvature of the tracks and their momentum very precisely. We can do particle identification, electron, muon, gammas, photons, sorry. And we do this thing called real-time analysis, that we reconstruct all these events online. So reconstruction of muons, pions, and kaons is excellent, but with this detector, electrons and photons are more difficult. If you'd go to an experiment like Bell 2, then they do a better job there. And taus is really challenging, because you have this huge backgrounds in our B production events, and tau decays include reconstructing missing neutrino momentum. So this is really, really difficult, and that's an experiment like Bell can do much better. And this will come back in the end, these difficulties. Okay. Are you still with us, or am I should make some break here to absorb this all a bit? Okay.
I'm really enjoying it.
Okay, I'm glad to hear.
But I understand if you need a break.
No, I'm all right. I'm having fun.
No, I'm seriously loving your slides. You should publish these slides. They're amazing.
Well, you can have them. About CP violation, there's another nomenclature I have to introduce, because we always speak of 3 types of CP violation. And this is all to do with the interferences that I was discussing before. When CP violation was first discovered, it was in 1964 by Christensen, Cronin, Fitch, and Turley. They did this famous Kaon experiment. And basically what they measured is that the probability of a K0 particle to oscillate, as we call it, into a K0 bar. You can make these particle-antiparticle transitions. So the rate with which it goes from K0 to K0 bar is different than the rate it goes back from the K0 bar to the K0. Weird if you think about it, but that's actually what happens. This is called CP violation in mixing, because you mix the B to the K0 to K0 bar, or sometimes called indirect CP violation. And there, if you look what actually gives you the effect, it's the interference of the dispersive and absorptive amplitudes for this transition. But I don't need to go in detail there. Then much later, in 1999, and this CP violation is actually this famous parameter epsilon. And the amount of that was 2 times 10 to the minus 3. So CP violation is, at that level, small. It's not like 1 for parity violation or charge violation. Now, then later, you could ask, is there another way of CP violation, or is this only in this, what is called this super weak force that was invented by Wolfenstein, I think? No, it was also found in directly decay processes. So in the decay of a K0 to pi plus pi minus, which turns out to be not the same as the decay rate of a K0 bar into pi plus pi minus, which is similar as this B to K pi that I showed you before. And in the kaons, this parameter was even smaller, because this was about a factor 1,000 smaller than the original CP violation in mixing. And in decay is called direct CP violation. And what you interfere there are different decay amplitudes with what we call these isospin 0, isospin 2 decay amplitudes. So that's another way of doing it. And then finally, in what we now use in B physics, is what was first discovered by the Bell and Babar experiments in 2001. And that's we call mixing-induced CP violation, which is kind of interesting, because what happened here, you produce the B meson. It can decay, for example, in a final state with a J psi particle, which is a charm anti-charm state, and the K short. Or the B particle can first oscillate or mix into an anti-B, and that can decay to the same final state, because this is a CP eigenstate. So it's accessible from both the B and the B bar. So you have these 2 amplitudes, direct decay or decay through mixing, and we call that mixing-induced CP violation, which is prominent in B physics. And that decay asymmetry in that specific decay mode is actually 0.7. So now we talk about completely different order of magnitude. Here you talk about 10 to the minus 3 and even smaller, while here in the process you talk about large numbers. And the reason that it's larger is that it's the 3rd generation. And what we have learned is that in all these processes, you need to have the 3 generations of particles present at the same time. If you don't, then your CP violation is 0. In order to see CP violation, all 3 generations have to be active, just for the same argument as I made before. An analogy. I wanted to do this, but I didn't go to Ireland. But the soup of the day in Ireland is whiskey. So instead of CP violation, there's also 3 types of flavor violation in my view. You could say a flavor violation in mixing or blending, as the Jimson is CP violation by blending. You have the direct CP violation, which clearly is a single malt, and then you have something very weird, which is mixing induced. And there's something I found actually when I was last year in Dublin. I happened to be there a year ago at Maynooth. There's this thing called Black Irish apparently, and yeah, I find this very weird. It says whiskey, spirit, and stout. I have no idea if you guys know this, but to me, I haven't tried it. But I think it suggests that the interference experiments can give very interesting results. So this is the 3 types of flavor violation that I really had wanted to try this time. Sorry that I wasn't there. So I will show you of these three types, some, just to give you a bit of a flavor what we are doing of the LHCb experiment, what we are measuring. And we are measuring them all now. The experiment is very complete. It works very well. And here you see, for example, the type 1 CP violation in mixing, which is where we now measure the decay rate of B, in this case, B or BS to BS bar, and the other way around. And there you get the interference between these two dispersive and absorptive amplitudes. And the way we measure this is we take a process where this B decays, like this here, a BS decays in a DS minus mu plus and a neutrino, and an anti-B decays in DS plus mu minus and a neutrino. So we know by the charge of these two things whether this thing was an anti-BS or whether it was a BS. And we know that at the beginning we produce them in equal amounts. So that means if we measure one more than the other, then the transition rate from B to the B bar was different than the other way around. So it's a very simple measurement. We just measure this asymmetry, the number of ds minus mu plus minus ds plus mu minus divided by the sum. And we do this for the process BS to ds mu and to BD to D plus mu. This is the charm system. And this sketch shows you typically how this works. We collide here the protons, and in this collision we produce a B quark and an anti-B quark. The B quark here hadronizes in the BS. This BS then decays to the DS, which flies again with a certain lifetime, then decays in the K plus, K minus, and the pion. And this thing here also has a DS plus and muon, and the neutrino we don't see. And the same thing here, but the only difference is KK plus is a DS, while K pi pi is a B plus system. Oh, sorry. So that we then measure, and we measure these asymmetries, and here they are. This is we call them the semi-leptonic, because it's a semi-leptonic decay, semi-leptonic asymmetries. Here is the one for the B, which is this one, and here vertically you see the one for the BS, and then this value is 0, 0, and what we saw before by the D0 experiment at Fermilab, so many years ago, there was some deviation, sort of deviation observed, but that actually went away, because here are the measurements that we see, and the world average is consistent with 0. And that means that this type 1 CP violation, which is the dominating one for the kaons, does not happen in B mesons. So the B to B bar goes at the same rate than B bar to B. If there is a difference, it's really very small. And that's contrary to kaons. And you see there, if you want to, I will give you the papers where you can see all these results if you want to look them up. So that's the situation on this type 1. Let's go to type 2, the direct CP violation. And here we use decay rates of what we call B to DH. D is a charm meson. And this H can be any hadron, like a pion, can be a kaon. We can see whatever systems we have. And if you now make a decay such that you would have a B meson that goes temporarily into a D bar 0 and a hadron, where the D bar further decays into a final state FD, whatever this is, I will show you examples. And that final state is also accessible with a D0 hadron. So the difference here is D0, D0 bar. It again means you have two decay amplitudes and into the same process, and they can interfere. Now, this one actually, from the B minus to D0, is a decay that is governed by the B to C transition, which is this one. While this decay here is governed by the B to U transition, which is that one. And now we take again the CKM matrix, and we see here that we have between these two, so as a phase difference, this weak phase, and this is this weak angle gamma that we had before in the matrix. So what we do, in fact, I say here an H and an F, and it turns out that you can make many decay modes of this thing. So this experiment measures them all. We have lots of students, lots of postdocs measuring all these things. And then we can measure this value, alpha of the weak force. And here it is. This is this alpha, it's gamma, sorry, gamma. Here we plot the value of the gamma using all these measurements. And we plot them here individually for BS mesons in light blue, B0 mesons in orange, B plus mesons in red, and all together. Now what we see is that we get a very precise value. So this actually, if you remember gamma, it's the apex of the triangle, and it's getting a very precise measurement. And maybe you could say, they don't all agree. Well, actually, if you look here, you see the 1 sigma and 2 sigma levels, and within that precision they do agree. But you could say, note the statistical spread into the BS, B0, B+, maybe something's hiding there. No evidence at all, but you can look into it. So that's the status of these measurements. Remember, in the end, what I said in the beginning, everything we measure with all these decay rates have to be explained by 1 degree of freedom in the standard model. There's only this 1 degree of freedom, and they all have to match. That's the challenge. Then we go to type 3, which is this interference of mixing and decay. And that is called often the decay time dependent CP violation. And what you do here is you create the B meson and the B bar meson. And for each B meson, you measure its decay time. So you plot for every event after how much time it decays. And then you compare the decay rate as a function of time for the B and the anti-B system. Now, this was first how Barbar saw CP violation. And in Barbar, I don't go into detail there, they created B bar pair that are coherently produced, which means that one decays before the other or the other way around. So you can get a time-dependent CP system that either is negative or positive in time. So this is this time axis. And here you see the decays of 1B to a final state F, and then the anti-B to the same final state. So it's a CP eigenstate. And you see that these decay differently as a function of time. And you get an oscillating behavior. So again, remember, I just always like to make this example. You produce a B meson, it decays directly into a J psi K short in this example, or it goes first to an anti-B and then decays to the same final state. And that's why you get this CP oscillating signal. You interfere the direct and mixed decay modes into this J psi K short. And actually there's a CP angle e to the I2 beta here. Now, why is that this number? This is the diagram that actually makes the mixing from B to B bar. And then you can look up what is your coupling, which here is a VTB, which is here a VTD. And all these couplings together then give you 2 times this angle beta in this CKM triangle. It's a bit complicated, but this is how you can kind of understand why this thing gets there, because there is a weak phase in this process.
Sorry, Marcel, just on this graph, you say B and B bar decay differently with respect to time. You don't mean that they have different lifetimes, right?
No. So what you see, you produce a B and a B bar.
Yeah.
And you measure them specifically into this final state. So it's not the lifetime of the B, it's just the decay rate into that specific final state. Yeah. Now, and the miracle of it all is if you add them all up, then you get, of course, the same lifetime. But in this specific state, they do something else. And in another final state, they do something else. And that's how we do it. So
it's not realistic to think there is CPT violation in this specific decay channel.
No. I mean, we do measure the total decay, the lifetime of the B and B bar. They're the same. Yeah, as far as we can see. So yeah, no, that's not it. No, it's just this time-dependent difference between the 2 decay modes, and you see it here happening, and it's a very clear signal that was discovered by Bell and Barbar. And it's actually due to this complex coupling in the CKM. And here is the LHCb signal. So by now, this was a discovery, in this case by Barbar. Now we measure it also. The difference between Barbar, Bell, and LHCb is that we produce B and B bar quarks in a big event where we also produce other particles, just to say it's not a coherent signal. So the nice thing of Barbar and Bell, that's a whole talk in itself. When you produce them in an EPR experiment. Because when they oscillate, if one oscillates, the other has to oscillate the other way. So they all oscillate in sync and move apart. And then one decays and the other decays into something else. And then you can measure these effects. But it's a beautiful EPR system to look into. Now in LHCb, the B hadron that hadronizes independently of the other B quark. So you can make one B meson on the other one. You can make a B plus, or you're making a B baryon. They're completely independent. And as an upshot, it means that we only measure for B particles. You know, we don't have this negative axis here in the experiment, so we only measure one side. We only measure positive lifetimes. But here you see a beautiful oscillation curve again that we see. Yeah, this is just a result of that. So you can do that for a final state, which is a CP eigenstate. This is this thing I just showed you, and this is the result. And actually, here is the other one. We can also do that for the B sub S. So this is the example, B0 go to J psi K short, but we can also do it with a BS particle, BS meson to J psi phi. And this is a SD bar system, this is a SS bar system. And that difference here means here we measure the phase 2 beta, and if you look at the diagram, actually in this case, you measure the phase beta S. So you measure another place of the CKM, again, a similar phase, but with another element of the CKM, which corresponds to this diagram. And the plots at the right-hand side shows you the precision of the state of affairs. And yeah, at this point, I just want to say, look, we're getting very close and measuring these angles to quite a high precise value. For example, here, this phi S phase that you see here. I say phi S, but it's a different name that we use for this beta S phase. Apologies. So this beta S is now a very precise value, very close to 0 that we measure with high precision. So just to say that we're doing all this, if you want to look up these measurements, they are here. And there's much more that I won't even go into detail. We could do B to pi plus pi minus, which is sensitive.
So can I just pause you quickly? Will
Say
these will these measurements improve with the next run of the LHC?
In general, my answer is always yes. We make much more statistics, but there's a little caveat that I'm personally want to look in. What we need to do experimentally in this thing is something called tagging. What I can show that here, I think. So what we need to do is when we measure B into J psi K short, for example, we need to know whether a particle was created, was it a B or a B bar? Because you create a B, it may decay as a B, but it can also decay as a B bar because it can oscillate. Yeah, and all these things are happening at the same time. But you need to know how this thing was created as a B or a B bar, and that's called Flavour tagging. And the higher the luminosity gets, the higher the intensity of these collisions. We now have maybe 40 collisions at the same time. It's very difficult to get this experimentally, this tagging process into shape. So this is something, yes, we should do better, but we have to work like hell to get it done. It's not easy. So yes, we want to do much better and get more precise. And there's more of them. Here is this decay B to pi plus is sensitive to the angle beta plus gamma. Because, okay, that's how this thing, it's beta plus gamma. In this case, you have BS going to K plus K minus, which is sensitive to 2 beta S plus, beta S plus gamma. So 2 beta S plus 2 gamma, beta S plus gamma. And in this case, it's BS to DSK, you're sensitive to BS plus gamma, etc. So we have all these things that we measure, which gives us all these angles, which in the end have to be consistent with one triangle and 1 degree of freedom in the theory. And here I just show you the curves and the state of affairs. So we're doing all these measurements, and we're collecting all the results. And yeah, this is somehow the conclusion of the CP violation step. So we're measuring this triangle with this rho and eta parameters, and we all bring it back to these measurements. And this apex of this triangle, it still seems to match pretty well. So we make many measurements. It becomes a precision measurement. Anything beyond the standard model, anything that shows up in these decay amplitudes that is not standard model should give a deviation. But the CKM prescription so far survives all these confrontations of this of the data. So far it's still all very consistent. I just pause if there's any question at this stage. Otherwise, I go to the last topic if you're still up to it.
Definitely still up to it.
We're still up to it.
There's
The last thing is the Flavour anomalies.
Mm-hmm.
which is, here you see the reason why this thing is called a penguin diagram. For those who don't know the story, it's a story where John Ellis was involved in a dart game, and he lost the game of darts, and then he had to, the bet was on that he had to use the word penguin in his next paper, and this is how we managed to get it in, and now everybody talks about penguins. So there's a long story, but that's in a nutshell. So let's go to these things. B decays. We've seen that in the standard model, this flavor changing decays where you actually change from one quark to another quark can only go with charge currents, meaning that you can go from a positive charge quark with plus 2/3 charge to minus 1/3, and all the interactions are charge current interactions. You go from plus 2/3 charge to minus 1/3 in any process. And the standard model does not have implemented flavor changing neutral currents. So a Z always decays into a C anti-C, S anti-S, B anti-B, U anti-U, and never to a U anti-C, for example. That doesn't happen. That's not in the standard model, and it comes out automatically. But of course, neutral currents can be possible through higher order processes. Right? And here they are, the penguin and the box. So how does it work? Basically, it's overall a neutral process, but it does involve these flavor changing charge currents. This W is here, but then at a higher order, here you couple the TT bar to a Z, and then you can get such a diagram based on the penguin. So as a higher order process, you can make these flavor changing neutral currents. And this is an example of decay B going to a K star, and B going to a K star and two muons. We will see that later. Or, for example, if you go to a BS meson, this is a BS meson and this is an anti-BS meson. Sorry, this is an anti-BS meson and this is a BS meson. And you can see that combinations of these charge currents can give you net a flavor changing current, which is net neutral because you go from zero charge to zero charge. We call this a box diagram and we call this a penguin. So these are the two types. But you see that this on the left, these charge currents, they are lowest order. They can go at tree level. These are higher order processes, the penguin and the box, so they occur less frequent. Hence, they are very rare. So here are two examples, A and B. The charge current and neutral current, as you see.
Have these flavor changing neutral currents been seen yet?
Say again?
Have these flavor changing neutral currents been observed?
Absolutely. Yeah. Absolutely, you will see them. Yes, absolutely. No, so what has not been observed is flavor changing neutral current at tree level. So at a higher order, yes, we do see them, but we don't have a single particle at tree level that's a flavor changing current. So if you look, for example, at this diagram here, there's no fundamental flavor changing neutral current here. Because at this vertex there's no flavor changing, but the flavor changing happens effectively with the charge current, which is hidden into the process. So these are the two. The charge current, which is tree, which is allowed. So you work with large decay rates. For example, a B meson going to a D meson, tau and a neutrino. These are the so-called semi-leptonic decays. And these are these neutral currents, which are suppressed because they're higher order. And we call them rare decays, and here you have a B going into a K and the muon pair or an electron pair. So to remember, the B to D are the allowed ones and the B to K are the suppressed ones. What we want to do is you can make a B to D tau neutrino or B to D muon and muon neutrino, and you can measure the decay, you can measure the ratio of the two. Because these, in the standard model, again, these interactions are identical. So this ratio has to be 1 in the standard model. It is 1. And you can also measure it instead with a D particle, with a D star particle. So experimentally, we can also measure this ratio, B to D star tau nu over B to D star mu nu. This thing has to be 1. So we can measure this ratio. And the same we can do in this rare decays. And we can measure B plus to K plus mu minus, and compare that B to K plus E plus E minus. And with a K on, we can also take a K star and we can do again this measurement. So we can do all these tricks to see how they compare. And now you have to think of this universality aspect, because universality requires these things to be absolutely sharply defined to 1. This is theoretically very clean. Okay. So let's go first to the semi-leptonics one with the B to D. These are the allowed currents. And you measure this ratio, for example. Now it's a little bit tricky because, as I said before, this involves taus. And taus are not our hobby in LHCb. Why is that? Well, here you see you have a primary vertex, which is the collision point. You produce a B meson, decays into a D and a tau. In this case, it's the D star, the D0, and you measure all these particles, but you have these missing neutrinos, and this happens in the midst of many other particles in the event. So this is hard to separate from the background. The muon case is easier, as you see here, but you have to measure this ratio. Okay, and then we also take the case where the tau can decay into a muon and 2 neutrinos, or whether you have the tau into 3 pions. You can do all these things together and just work hard. Here's the result immediately. There are many measurements over time, Babar, Bell, LHCb, and these are calculations of these results. And just to confuse you, I said this has to be exactly 1 in the standard model, which it is. Were it not for the phase space factor that we don't really call standard model, but in practice, because the B to tau is a less mass difference, there's a phase space factor where this number actually ends up at 0.26 something. But this number, for all purposes, standard model, we call it 1. But it's not 1 because of boring phase space. Now, the point is that we see here in this plot, we see some measured values of RD star, where we use the D star particle and we use the D particle. Many measurements. This is the standard model calculation in black here, and this is the average of the measurements. So this is interesting, you tell me, but if you calculate sigmas, this is 3 sigmas from the standard model. So this is something that has been long-standing, and it's intriguing, and it's still there. You could ask, what could it be? The standard model has this the W here, but you could think of models with a charge Higgs. You can think of something with leptoquarks. You can think of many things. But what you have to keep in mind is that this B to D is the one which is allowed. So that happens a lot. The fact that you would possibly see something beyond the standard model means that this thing beyond the standard model is also big. It's happening a lot. So one would not expect it there in the first place. On the other hand, it's a potential large new physics effect, but it involves 2nd and 3rd generation particles. It involves taus and muons. And the 3rd generation, maybe we said if you go back to the very beginning, maybe something is happening there with the Flavour asymmetry. We don't know. So, but that's one to keep in mind. Then we go to the other one, number B, the rare decays. You go there, I hope. And this is the diagram. So we take a B to a kaon and 2 muons, and it's a penguin diagram. And these are tricky decays. So now that we have to call in the help of our flavor physics theorists, because things are not so easy anymore. We have form factors, we have a lot of mess. We have an effective Hamiltonian that we use. Now, few things are easy. There's a weak coupling constant in a weak decay, that's okay. We have a VTB and a VTS, which are the couplings of the B quark to the T quark here and the T quark to the S quark here. That's also fine. But then we have things which separate short and long distance effects in this, because we have lots of gluons running around and the strong interaction. It's a bit of a mess. But we like to factorize these in Wilson coefficients, and we call these things CI. And what we then do is, sorry, I confuse you. We plot the invariant mass of the amount of momentum going from this vertex to this vertex, which is the Q squared of the dimuon pair that we plot here horizontally. And then we measure how often the process happens in this spectrum here. Now, and then the interesting one is this region, and this region is driven by things called Wilson coefficients C7 and C9. What they are is not so important now. It's a vector. The C9 is a vector, and the C10 is actual vector contribution. C7 is like a photon contribution. And these spikes here just show that you actually produce a Q. You produce a a dilepton system that resonates. Here, if you produce them by a photon, you get a resonance behavior. Here you have a J psi, and here you create a dimuon pair as a psi to s. So these are resonance, but this area is the interesting one that we want to study. And we do that again in 3 ways, and I'll go very quickly, otherwise I confuse you too much. We have 2 ways to study this system, either by measuring just the decay rates of the process. And this diagram we can do with B plus to K plus mu, B0, B plus to K star, B0 to K star, 6 ways to do it. But when we measure decay rates, we have large theory uncertainties because this thing here is a mess. We can also do something that we don't study decay rate, but look at the angular distributions of the particles. That's getting better theoretically, and I will comment on it. And the best thing by far to do theoretically is just to do the ratios of muons over electrons. That's theoretically robust, but has less statistics, as you will see. So we do all 3 of them. Quickly, here to go to decay rates. These are 6 processes that we measured. And the only thing I want you to take away is there are theory calculations and there's data. And maybe you see it, but the theory calculations always tend to be higher than the data. So here are the papers, and the conclusion is the branching fractions related to this transition are consistently lower than predicted. Is it an anomaly, or is it a common issue with this theory uncertainties, which are 20–30% up to the theory community? So we cannot conclude from this. Second one, angular distributions. We take here a B particle decaying into mu plus mu minus or E plus E minus, and at the other
Sorry,
side.
could you just go back a slide?
Yeah.
Why do you need lattice for this?
Why you need to?
You have some standard model lattice results, but you also seem to have. Do you also have disturbative results?
I missed the word. We have lattice results, and we have light code.
And you also perturbative.
Yeah, so the problem is these processes, they are not just perturbative. We have these things called the light cone sum rule calculations. We have lattice calculations because we have these non-perturbative effects there that you have to take into account. So it's
what are the non-perturbative effects?
So if you go back, what I didn't show you, have all these this process here has also many gluons running around. So these things called form factors that we have to deal with. And we don't know their value. They're only known to 20–30%. So how often does this happen, this process? Of course, we have here we factorize here what we call the short distance effect and the long distance effect. And this long distance effect, these OIs are operators, which are given by form factors. And that you have to calculate them somehow or measure them. And one way to do it is using these, using light-cooled sum rules or using lattice. Does answer the question? Because this is not,
yes.
It's not simply perturbative because you have to do more. It does have, it happens at 5 GeV, and you have lots of gluons. But it's an art in itself. There's a whole theory community looking into these things. And the conclusion is that, again, we don't know. We have an anomaly. The theorists have to work, and but we cannot conclude.
So just again, could you go back? There's a gap on these top 3 graphs where you don't seem to have any theoretical calculations. Why is that?
Yeah. So that this gap is so. This region here, as a function of q squared, momentum flowing to dimuon pair, is the rare decay rate. Here, at this point, what happens, you create actually a J psi particle instead of 2 muons. So that is called the resonance. And here, it's a whole different story. Here we expect no new physics at all. It's not a rare decay process, and we use it actually as a calibration peak. And for some cases, you can actually try to measure here again, but typically we have this one and here the high mass region, and these are the 2 resonances that are sometimes just excluded from the plots if you look. So that's this. Oh, this region here is the excluded region because of the resonances at the J psi and psi to s. Because there it doesn't make any sense. Okay. Then the angular distributions, and then I'm slowly coming towards the end. We do some trick where we say we have a B, it decays into a mu plus mu minus, or into a K star, which decays in a kaon and a pion. And what you can say in this event plane that we create, we measure the angle between these planes, and we measure the cosine of this theta K angle here. We plot that, we collect all the event statistics, and then we just calculate these red areas, add them up, the blue areas, subtract them, and then the relative number we call P5 prime for some crazy reason that you can ignore for the moment. And we plot that variable, so this counting, as a function again of this Q squared, which is the momentum flowing into the Dimus system. And again, here we're interested in this area of the rare decays. And then we see something here where the theory, where the experiment deviates from the theory in this case, which is again a 3 sigma thingy. Then we went from the B0, we did the same with B plus. It's less significant, but somehow it's a consistent thingy. Then we went to also the BS to phi, the third one. So this is the first one, the second, the third one. We plot them here together, standard model calculation. And this is then the interpretation in terms of this Wilson coefficient, which is this C9 vector coupling. And we see something like this. Okay, that's, again, it's a bit better, but there is something called charm loops, which can occur here at this vertex. You can produce a CC bar thingy with a lot of gluon interactions involved, and the charm loops can actually mimic a shift of the C9. So again, we send it to the theorists, calculate, and it's too early to conclude anything. Yeah? We see something for the moment as a deviation, but it can be caused by standard model based charm effects that we don't know. Again, unclear. And then the last one, we do the ratio of muons to electrons in the same decay. So we measure B plus to K plus mu mu, B plus to K plus EE, and we measure the ratio, and the same with K star. And then remember that I told you in the beginning, electrons are also not great for LHCb. Muons are fantastic, electrons are not great. Why is that? Electrons do something which is called Bremsstrahlung. So they are produced here in the vertex detector, and if they go through material, an electron passing through material actually sees the atoms in the material, and it breaks, and it sends breaking photon radiation. So this electron sends out photons along its path. So we have to measure to get the momentum of the electron. We measure the charge track, but we also need to correct it with the photon energy, and that is also not a great procedure. So if you want to compare the precision of electrons and muons in a mass of a particle, in the J psi, for example, going to EE or mu mu, then the blue thing here is how well we do with muons, and the red thing is what we do with electrons. So we're struggling, not easy. So again, you know, this is the great one to measure, but there we lose precision. Murphy, thanks. So here it is. Again, we look at this region of the Q squared. We are March 2022. We publish in Nature. This is the electron one, B going to K. This is the K plus EE, and this is the B to K plus mu mu. Much better than this one. And if you actually get the ratio out of it, it turns out that this is a very interesting number, because what we get is, and then, okay, here's a comment. We use these resonances to calibrate, to test that our procedures are okay. So we do all that. And this is the number we get. We call it RK. It should be 1. Here is the number 1. This is this Q squared. This is the B plus to K plus. This is B0 to K star. And here in black, you see the values that LHCb measured by that time. So this was now getting really interested, because now this is not theoretically dirty. This is very clean. If this is not 1, then we have something. So we got very excited here. And we're now in March 2022. We're adding up everything we had at the time. This is the version, the value 1. These are the measurements. So at that point, we thought, holy God, this is interesting. There were many newspapers coming out. Experts revealed cautious excitement, as it was called at the time. So many papers actually published on it. Many people got very nervous. And we had this thing, and we had this P5 prime thing. And that together said, yeah, what the hell is going on? And then came December 2022. Now you feel the bummer coming. We decided to do this RK and RK star simultaneously, the two decay modes, because that made the analysis a bit cleaner. Okay. So again, the same process, and we call it now B to S mu over B to SEE. This was the result in March, and this was the result of the same channel in December. Very consistent. We cleaned up the analysis a bit better, and we did something with these electrons. We did a new inclusive data-driven misidentification method, because sometimes a pion in the experiment looks like an electron, or a kaon looks like the electron, and make a mistake.
Mm-hmm.
Now, what did we find? If you look at this plot here at the bottom, so the December one, we see some greenish things here happening, which was not there before. Here it was in the orange part.
Yeah.
No, sorry, in the blue part. And here the muons, they stayed the same. So actually we had a little bit more electrons into the system here, which changed the electron channel a bit.
Mm-hmm.
What happened? The ratios became 1, consistent with 1. So that part of the excitement has gone. It's no longer there. Those electron channels are now 1. But if you look back, there's something weird happening with the muons still, because we were excited about the muons. In the branching ratios, they were too low, and the angular observables, they deviated for the muons. But then when we measured the ratios, the ratio was too low, and it was not 1. But then the electrons changed. So it looks like, if you take that from a big distance and don't look in detail, that now both are wrong. So instead of both showing a consistent standard model, something weird is going on. So still, this is a summary of all the data that we have here for this for the muons, the theory, and all the measurements that we see. Something is still not understood. Could be theory uncertainty. The muons did not change, where we thought something was happening to the muon, but the electrons changed. And we have to give the ball partly back to the theory community, and there's much more to come in the coming run 3, as I will say in the last bit. But a suppressed penguin is not a depressed penguin, so we're still happily analyzing all these data. Me in March 2022 was this. Me in December 22 was this. So we all kind of went to an emotional roller coaster if you take this stuff seriously. What is going on? We don't know. So my outlook and conclusion is run 3 has just started. We have a whole new experiment, basically, new trackers. We have real-time analysis. We have lots of physics program, a beautiful detector. And the conclusion is that to me, the origin of the generation structure meta-antimatter asymmetry is still not fully understood. Is it caused here? Is it caused before? Is it caused later? I really don't know. I'm really curious about it. I want to figure out as much as I can. The CKM paradigm still stands. Experimental tests are getting more and more precise. And these BDK is a really sensitive tool for BSM searches using these quantum fluctuations. Semi-leptonics with taus are really intriguing, because that's this B2C effect. What is going on there? The rare decays with the muons, they show deviation from theory, but the electron-muon universality ratio is now consistent. And I'm looking forward to more results from LHC3. And again, we have improved a lot our electron reconstruction, so we should get much better results. Thank you for your attention. I've been talking so much to you, and you're still there. So I'm really great.
It was fantastic. Thank you so much. Yeah, what an amazing talk. I really enjoyed it. Thank you.
Thank you very much. Thank you. Thank you for giving it.
If you still have some energy, I have questions.
Sure.
So could we go back a few slides when you were, let me see. Yeah, here is even good. So the issue was that LHCb couldn't do a very good job with electrons. Did Bell or Barbara have the same calculations or measurements that you could compare with?
So I had them somewhere.
Yeah.
I have them somewhere just to say where I put them. No, I should go to the other one. So the answer is Babar has older data. Where did I put them? I have them somewhere. Okay, it doesn't matter. Yeah, so the problem with Bell and Babar, as you call it a problem, it's the experiments are much cleaner.
Yes.
In general, they can do B zeros, they cannot do B sub S because the energy of the beam doesn't work for B sub S, the time-dependent analysis doesn't work. So they do the B sub D, but it's an electromagnetic process. So they create a very clean BB bar system, and they can measure electrons much better than we do, but have much less statistics. Because the way you produce B mesons with proton-proton interactions with this strong process is orders of magnitude more data than they have. So what we have is the power of statistics, or they have the power of cleanliness.
Yeah.
Babar stopped many years ago, so the data that they had is whatever it is. And Bell 2 is still in the taking off mode. It still hasn't got there, but certainly it's going to look at that, and it's come with data. How will it compare to LHCb? And we have to see, but they still have to do it. That's the answer. So from the past, they don't have the statistics.
Yeah.
Now they're creating they're collecting statistics with the beam. They're having some issues, I understand, to reach the highest luminosity of the collisions because they really need the super tiny beams with high intensity to produce statistics. So that's their challenge is more the accelerator to create the events. And our challenge is to deal with the mess.
Do you know when we're expecting data from Bell 2?
It's ongoing. So any year more, all the time, they're taking data. I had this number somewhere. Where did I put it? Okay, I thought I had it. Anyway, man, cannot find it.
Yeah.
So yes, but it's they're certainly doing it, and it's competitive. It's certainly competitive. In general, my status is always something which is very rare decays. For example, there's other things I didn't talk about. B2 mu mu. For example, this is what you call a forbidden decay. Now, that you have to do with LHCb because there you simply need the power of statistics.
Yeah.
If you go to things with neutral particles or with taus, in due time, so also this B to D star tau, they should be able to overtake at some point. So here in this plot, for example, you see the results from Bell are similar in 2015 than we have in 2022. So there, if they get more data, they should overtake LHCb simply because the tau is in high luminosity is a mess.
Yeah.
The tau decay because of the missing neutrinos.
Yeah.
So it's a nicely yeah, it's how you call it complementary.
Yeah. No, absolutely. Yeah.
Yeah, I'd say they have the different specializations. Neutrals and taus go to Bell 2. Very rare decays and something with muons go to LHCb.
Yeah, I mean, you keep on hearing about these Flavour anomalies, and kind of the feeling from the community is that it's not
I tried to give it as clean as I could, including my own emotion into it, because we certainly went through a roller coaster.
Yeah. No, I really appreciate that. Yeah, because I mean, that is a real part of being a physicist, and you did really communicate it. But you got me really, really excited because I actually I was working on Froggatt-Nielsen mechanisms, and you can explain a lot of Flavour anomalies with it. But as kind of the excitement went down, I thought, you know what, it's not worth it. But yeah, you got me all hyped up now. I'm thinking.
So I should be fair because I'm also still excited, and but there are these things, decay rates, they are really theoretically uncertain, so we cannot say.
Yeah.
The angular distributions, they have this charm loop, so we also cannot say. And the thing that's really robust, we screwed it up with this electron background. So if you ask for the future, what I'm most worried about is the potential to make mistakes. It is the events get more and more complicated and high luminosity.
Yeah.
And we really need to keep on learning lessons for calibration procedures. Because what happens is it's actually a very funny thing. So we use, I think I wrote it somewhere. So we use this, we want to understand the K mu mu and KEE in this region here.
Mhm.
And said, look, at least we know that we have these two peaks here. We have lots of data for where the thing goes, the muon, the muon comes from a J psi or from a psi to S,
Mhm.
or the electron pair. And here the ratio has to be 1. So what we do a blind analysis to make sure that in this region here, we understand what we're doing.
Yeah.
And it worked brilliantly. We've measured exactly 1.0.
Mm.
Now, why is that? And here we actually had to correct it because we found some little electron background.
Yeah.
Now, the little electron background was also present here. But since we had so much statistic, that particular background was an absolute amount, didn't do shit, to say just flat. Well, here it was a little on a small signal. So here we felt it.
Yeah.
And looking back, how could we have missed it? You know, I could myself hit in there.
Yeah.
Because and it's a little thingy that we changed our selection criteria a little bit. We saw a dependency, and my God, what is happening? And there we saw some backgrounds that we had missed.
Yeah.
Yeah.
Yeah. I mean, that's the joy of physics, right?
Well, at the time, it was not really a joy, I can tell you.
Yeah, I mean, to me, like as I said, you got me all excited again. It's not that, you know, oh, this could really be something, but it's that if I try to understand this and I try to find a theoretical framework that would fit this in, think of the amount of physics I'll be learning.
Yeah. So what
yeah.
I personally like, but that's really taking a long distance, is we know in general that also with EDMs, yeah, you're very sensitive to very high mass effects.
Yes.
Now,
Yeah.
to me, the EDM is just a bit too far away. The difference between what you measure, it's just an enormous difference. And here we somehow are a little bit closer to this TeV scale effects that we may be sensitive to.
Yeah.
And it's in general, the sensitivity is there if the experiment does a good job. So
yeah.
Find a nice, if you have a nice idea, find a signature. And where do we look for it? Now, the other thing is, I didn't talk about the beta mu mu. And because also there we had some excitement because of the same thing. This is again the B to S transition, but then it's again suppressed by this helicity suppression, because the way you produce the two muons, they're the wrong way around.
Yeah.
Also, there at some point we were seeing a little bit of deviation, which was consistent with this, but then the significance is much less. So also there we want to look. We want to look to BD to mu mu compared to BE to BS to mu mu. We're looking for B to EE, which should be absolutely 0. Yeah, many things. Yeah. Also there is stuff to do, and then there's also CP precision measurements. Absolutely, yeah. So the experiment gives a lot of potential to study. Yeah. But at the moment, it's open. Absolutely, yeah. I mean, you really made me appreciate how much physics there is in LHCb. Yeah, it's a lot of physics. That's what I like about it. That's what I like. Yeah. I'm going to let other people ask questions if they have, because I still have questions, and yeah, if you have the energy. But yeah, I want to let people ask questions if they have any.
So you mentioned that the Froggatt-Nielsen mechanism can try and explain these flavor anomalies. Could you also try and explain it with a 3 Higgs doublet model, where say each Higgs couples to one generation of the families?
Are you asking me or Marcel?
Either.
I think she's asking you.
Oh, okay, yeah. Yeah, so no, you can't. So actually, Marcel, you had a plot where you had a charged Higgs or a leptoquark giving an explanation for I don't know which slide it was on.
Yeah, it's a B2C.
Yeah, there we go. Here, yeah. So the kind of 3 Higgs doublet model you're asking about, Jasmine, are you asking the private Higgs model, or I guess the original one that Weinberg suggested, that for each family you would have a Z prime, a Higgs doublet?
I guess I just mean in general, can one construct a 3 Higgs doublet model?
If you have the Z2 symmetry that you normally impose in multi-Higgs doubler models to get rid of the flavor changing neutral currents, then you can't.
Okay.
Yeah, because you would need, so in these Z2 symmetric scenarios, you have, let's say, in the type 1, for example, you have the one Higgs doublet coupling to everything, in which case you're very much like the standard model situation. So the couplings to the third family and the second family would be exactly the same. If you have the second, one doublet coupling to one family, a second doublet coupling to another family, the mixing between the families is not allowed. So you won't be able to explain this again. You would have to allow for, well, the aligned 2Higgs doubler model would definitely work here. Yeah, so, and I'm guessing, yeah, this plot that Marcel has here would be an aligned 2Higgs doubler model with the charge Higgs.
Yeah, that makes sense.
I'm trying to remember, there was an issue with the charge Higgs.
Yeah.
Related to the lifetime of, now I forget which other decay it was. Because the problem with all these models is you don't have to make it work for this one, but you should also not, create problems with all the other ones.
Yeah, yeah, a charge Higgs, because it has not been observed, you would have to, if you predict it, it would have to decay very, very quickly inside the detector, so before it even reaches the ecal or anything. So, but yeah, possibly the lifetime would be too short, but also it would have to be heavy because we haven't observed the light charge Higgs. So,
and I think, was it now the lifetime of the B sub C or so? There was a problem with the lifetime of, but I forget which one. That it, but I mean, problem, there was a tension, then you have to, tweak it such that it can still describe both.
yeah.
Now I remember there was a lot of excitement about from this PS3 model from our Zurich colleague. Names, I forget his name. The theorist from Zurich. No, I feel the name is gone.
Sure, yeah, and I know. Well, I was in Morion a couple of weeks ago, and Andreas Krivillian was talking about these anomalies. Is that him? Okay.
No, it's not the same, but it's another one. Yeah. Yeah, but indeed, the stuff you're looking at, I'm sure has interesting possibilities and connections. I wouldn't know by detail; it's not my business. But if you have some papers that you would like to refer me to, I'd be very interested to have a look.
Yeah. So since the conversation is getting quite specific, maybe I stop the recording and we let people go, because if you have the energy, I would still like to discuss further with you.
Okay.
Yeah. So let's thank our speaker again, and I'm gonna stop the recording.
And thanks everyone for being there. Appreciate it.